back to the second video in this sequence, and this one will be going through some examples of actually computing the divergence of some three-dimensional vector fields. So in this first example, we have three different vector fields. We'd like to compute the divergence of them. This first one, we have a radial vector field, x, y, z, and so we would expect, as we've seen before, that the divergence is positive for here. In the second one, we have a variation of a rotation vector field. And in this third one, we have yet another variation of a rotation vector field. As you can see, we have minus y and x in the first two. The z component is going to change it a little bit. This is what's called a spiral flow vector field. But we'll compute it's not really important to know the names of these. We'll be able to compute the divergence of them regardless. So in this first one, I'm going to use this new del operator notation. Del dot f is partial with respect to x of the x component. So maybe I'll write it like this: partial with respect to x of x plus, right, this is a dot product, so plus partial with respect to y component, partial with respect to z of the z component. So each one of these partials is 1, and so this is just 3. So that is, the divergence of this vector field is constant, and it's positive, which means that at any point in this vector field, the vector field is expanding outward from each point, and this gives us some measure of how much it's expanding outward. In the second one, we'll do the same thing. Del dot f, partial of minus y with respect to x plus partial of x minus z with respect to x plus partial of y with respect to z. So as you can see here, there's no x's. That'll go to 0. This should be a partial with respect to y. Hopefully you caught that. Partial with respect to y. Of course, there's no y's in x minus z, and so that goes to 0. And lastly, partial y, partial z will be 0 as well. So this is 0. And this is what we would expect from a rotation field like this one is. Rotation fields have no divergence. They're not expanding out. They're just rotating. And we can see that with this calculation. So lastly here, we have a variation of a rotation field, only it's sort of spiraling upwards because of this z component. So let's see how this works out. Del dot f, partial of minus y, partial x, plus partial of x with respect to y, plus partial z with respect to z. So these first two components give us 0, and the last one we get 1. And so this has a divergence of 1. So notice that there's no contribution from the x or the y components of my vector field, which means in any plane we would have 0 divergence. But since this vector field has the z in its z component, it's expanding upwards. And so the net effect of this is that the vector field is expanding less so than this first one, but still expanding at every point. And so it's not too bad to actually calculate this. Let's jump to divergence of a radial field, just in general. We saw this in this case. Here we had a radial field where I'm not dividing, I'm not making it smaller as I go out. Right, these are going to be expanding outward as we go. Here we'll take a look at another radial vector field. It might make sense to remind you of the radial vector fields, right? Can be written as r over magnitude r to some power p, if you remember that. So here's one instance of that. Remember that in this definition r, we just take this to be the point x, y, z is r. And so we're going to compute the divergence of this. In order to do that, we're going to need the partial derivatives with respect to x, y, and z. And so why don't we take a look at partial with respect to x of the x component of this vector field. That's partial with respect to x of x over this scalar, square root, and I'm actually going to write this as to the 1/2, just to save some notational. X squared plus y squared plus z squared to the 1/2. So partial of the x component with respect to x. And we can compute this by the quotient rule. So the derivative of the top is 1 times the bottom. So we have x squared plus y squared, z squared to the 1/2, minus derivative of the bottom. So that's 1/2 x squared plus y squared plus z squared to the minus 1/2. Don't forget we need a chain rule there, times the derivative of the inside, so times 2x. That's a 2, not a partial. Let me get my curl in there. So those derivative of the bottom, and then times the top, times another x, all over the bottom squared. So that's x squared plus y squared plus z squared. And let's try and simplify this a little bit. One, I see a lot of this x squared plus y squared plus z squared. Remember, this is magnitude of r, is this x squared plus y squared plus z squared. If I square it, I get exactly x squared plus y squared plus z squared. So what we have here, this is magnitude of r. Here it looks like we have magnitude of r raised to the minus 1 is this, because it's to the negative 1/2 rather than just the 1/2. So this is magnitude r to the negative 1. And then this 1/2 and this 2 will cancel out. We should have an x squared there. So putting this all together, it looks like we have magnitude r minus, let's get those x's in there, minus x squared magnitude r to the negative 1 all over, and down here we have r squared, magnitude r squared. Forgot my vector here. So just simplifying this a little bit further, I am going to, it looks like I have this r to the negative 1 I can put on the bottom, but that means it'll affect this. So what I'm going to do is I'm going to essentially factor out magnitude of r to the negative 1 and then distribute that to the bottom. So what this will look like is magnitude r squared minus x squared all over magnitude r cubed. So that's what the partial derivative of the x component of my vector field looks like with respect to x. Now this radial vector field is highly symmetric, so when I take a partial with respect to y of the y component of this, it's essentially the same as what we just did here if you replace every x with a y. And so I'll just kind of skip to, hoping you see that symmetry there, I'll skip to what this comes out to be. So del dot f, the divergence, is, so partial with respect to x of the x component, that was what we just calculated above, r squared minus x squared over r cubed, plus partial with respect to y, that's going to look like magnitude r squared minus y squared over magnitude r cubed, plus partial with respect to z, magnitude r cubed minus z squared all over r cubed. So there's my divergence. We can actually simplify this quite a bit. Notice I have, some patterns here. In particular, I can separate each one of these fractions and get, so if I just pull off the magnitude r squared over the magnitude r cubed in each one of these, I'll have 3 of those. 3 magnitude r squared over magnitude r cubed, plus, what'll I be left with? It looks like I'll have, actually maybe I'll say minus, I'll distribute this negative out. Notice how there's a negative on each one of these, so I'll say minus, looks like we have x squared plus y squared plus z squared all over magnitude r cubed. In parentheses just to be super clear. And then this x squared plus y squared plus z squared, well, that's none other than this is magnitude r squared. And so here we pick up another magnitude r squared over magnitude r cubed, which simplifies to 1 over magnitude r. So let me just do that. So this is 3 over magnitude r minus 1 over magnitude r. And so we get out, this is 2 over the magnitude of r. So it actually simplified really quite nicely. This is the divergence of that radial vector field. And in fact, it's not too hard to generalize this to that specific class of radial vector fields that we've looked at in general. So let's state a theorem past this example. So we looked at one class of radial vector fields that look like, so I'll say extend to radial vector fields that have the form, these all have the form r over magnitude r raised to the p. And I won't go through the whole derivation of this, but I'll just state the result that if f is from this class of radial vector fields, r to the p, then the divergence of f, dot f, is in general 3 minus p over magnitude of r to the p. Notice how this generalizes this past result. Here my p was 1. I'm just dividing by magnitude r, so my p is 1 in this case. And so I end up with 2 over magnitude r to the 1. And this actually extends back to over here. Here I'm not, here, this one. This is from the same class, but here my p is 0. I'm not dividing by a magnitude of r at all. That is magnitude r to the 0. And so that'd be 3 minus 0, that's 3, over magnitude r to the 0, that's 1. And so I just get out 3. So from 3 to 2 over magnitude r to, in general, 3 minus p over magnitude r to the p. And that's how we can deal with divergence of these radial vector fields. Pretty nice result. All right, join me next time where we'll take a look at curl.